So, I suppose my emails from earlier could use some elaboration. And I certainly have time for that today. So, as some of you may know, I was spending fall break in Southern California. And yesterday, Monday, is when I was returning here for the plant. So while traveling back, everything was going very smoothly. Went all the way to New Orleans, and then first half of the drive back here to Hattiesburg. It was all fine until I entered Mississippi. Something about crossing the line. Because you need to go awry. So I shortly after entering it, I pulled off I-59 into the Welcome Center rest area that they have there. And when I was coming to a stop, something felt funny tire-wise. And something I'm hypersensitive to because I always seem to have tire issues a lot and just curse that way. And it's not with my car, it's cars that I rent. So the equal opportunity curse. So I get out and I look at the tire, and driver's side front tire has a terrible sidewall bulge. Like it was big, like okay, it could blow any second. So like, okay, great. Now what? Because I'm not safe to drive on something like that. And the security guard at the rest stop graciously offered to put my spare tire on. Okay, great, but we cannot get it off. Yeah, didn't have the proper tools because whoever owned my car before I bought it slightly used with some aftermarket wheels on it, but got the right socket to unlock the lug nuts, and that can't be found anywhere. It just doesn't exist, isn't it? And so she suggested I take my chances and drive this unstable car to Walmart next exit in Picayune and see if they could help me, and they could not. And they suggested, well, maybe I come back in the morning when their full auto department is open, then maybe then they can help me. Okay, I guess I'm stuck here for a night. Go online, give myself a hotel room, and okay, well, I have no working vehicle. Maybe there's this is Picayune. Maybe there's a Uber driver that can give me a ride. I don't know. But first, I gotta eat something. And by then it's like 9 p.m. So I walk from Walmart to McDonald's to the truck. Take care of that. Then on my way back, it's like, well, move along the block. I'm already exhausted and hot. So maybe I can just take a shortcut across this grassy field. It was a grassy field at first, but then I started sinking. Got muddier and muddier. And by the time I decided to use the turn back before the mud swallowed me whole, I decided I wanted to keep my shoes. If it was that much mud that I'd take a step and my shoe would not come with me. And then I would look, and I could not see my shoes in the mud. I had to reach down in there and find them. And I did, not sure why, because they're no longer useful shoes. So walked back, well, not barefoot, but by my soaked socks to the car. And I was like, oh great, well no Uber Lyft driver is gonna want to have me in their car with my feet and bottom of my pants are totally soaked and muddy. And this is where it was actually a blessing that I have a lot of junk in my car that I really should clean up, but it came in handy, like just cleaning off my shoes and everything with mud. And also, I had some flip flops that I forgot about. So I didn't go find new shoes in the spot. And I'm like, okay. So that crisis averted, a self-inflicted crisis. Let's get a ride. Nope, no drivers. Call a hotel. Any suggestions? Nope. Can I cancel reservation? Nope. So I chance it and drive on this shaky tire there. Got some sleep, not a lot. And then at 7 a.m., let's go to Walmart and get this thing done. I guess we'll look at it like, oh, we can't help you, we can't take those off. Like, you don't have the tools for it. Walmart. Go to this tire place, and thankfully at 7 a.m. we're open. I go there, and sure enough, they're fine. They put a spare tire on, no problem, no charge. Like, okay, I'm on my way. Done, right? Done. I think back towards like it's 9. Like, oh, I need to get gas. All right, let's do that. Get out, and this tire at the tire place put on was going flat. You think that his tires are her life, and that they would check something like that?
That's why there's no charge.
Okay, yeah. Well, they want to get rid of me. Like I even tried to tip him, and he walked away. Both days were, yeah, almost kill me. Like, death number 2 out of 3. I'm not kidding. So yeah, they put a flat tire in my car. So got that filled up. So good thing I happened to need gas, or I wouldn't have known, and who knows what could happen. It's like good thing I happened to pull off at a rest stop to find that that tire was gone. Well, I'll just drive on for 5 months more, but so. Yeah. So finally on the way, and then just as I'm getting here, about to pull off on the party exit, my right flip flop slips, which makes it hard to operate a gas pedal or brake. So I had to think quickly and just like kick it off, and so I could still drive before something horrible happened. So I have a new tire ordered, and so on our forced holiday of Thursday, I can go and get it put on. So yeah, that was my misadventure. Lucky 3 times over, but nothing really terrible happened. So, go figure. Yeah. I think for someone like me who tends to think like everything happens for a reason, I'm still really scratching my head over all this. And that's the bit. It could have been a ton worse. It had many opportunities to be a lot worse. That's what's scary about it. Yeah. Anyway, and here we are. So,
Here you are.
yeah.
Driver shoot.
Yeah. Yep, turning my very exhausting all for options. Okay, so also remains that I'm still awake because it's been a day full of meetings at my other class. Right. Spherical Bessel function. Which I started feels like forever ago during our last class. Well, I guess it was a week ago. Okay. Most of those functions were lowercase version of Bessel functions. Really just Bessel functions scaled by basic function of x. Now, what was done last time was deriving power series representations of these spherical Bessel functions. And from those you can see like what happens for x particularly small, what happens if x goes to 0? Or what if x is going to infinity? So what happens is for small x, like x going to 0, all the terms in the power series can be neglected except the first one, which is just reduces to 1. So you get these. It's the expressions that sit outside the power series. I don't know if you'll have seen this notation. I don't recall if I've used it in this class, but double less than sign. So that means much less than. I know that's a really rigorous definition, but and then this is when we have much greater than, double greater than sign. And that's often done with these kind of functions is because it's have very complicated expressions, but if we can at least get a good approximation for small x or large x, that can be helpful. Now, as for the other spherical Bessel functions, these Hankel functions. So recall that these functions were defined as complex values where the real part comes from the spherical Bessel function of the first kind, and the imaginary part comes from the spherical Bessel function of the second kind. Now, these Bessel functions are finite as x goes to 0, as we can see here, whereas these are going to infinity as x goes to 0. So, so for these spherical Hankel functions, these are the dominant terms. These are so much larger for small x. So to get the small x approximations, we can just neglect the real part and take the imaginary part. Now for large values of x, these so the regular Bessel functions actually behave like trig functions. So the standard Bessel function of the first kind involves the scalar multiple of the sine part, and then for the second kind we have this cosine part. So now we just scale them, and these are what so for large x, these are decent approximations of these spherical Bessel functions. And then by taking this to be the real part and this to be the imaginary part, then we get these approximations of the spherical Hankel functions. And I'll just make a quick comment here that of this fundamental identity. E got theta, cosine theta, cosine sine theta. What happens here is here we have because here we have the real part and this imaginary part, so we're multiplying this by an I. But that means if you factor an I out of this and this, then you get what you're left with after you factor out like a minus I for this function and the I for this one. You get an expression of this form. And then you can condense that to this complex exponential, and that's how these complex exponentials come into play. Notice we have e to the I x minus n pi over 2 here and here, the same arguments that we have here. Now we should be careful about when we use these. The larger the index n is, the larger x needs to be for these approximations to be useful. We're certainly neglecting some terms here, and if we don't choose x large enough relative to n, those terms might not be so negative. I should probably preface next comment with an apology that this is something that makes sense in my head, and hopefully it will make just as much sense out loud. But like I said, that's up to you. Okay. Now, if we were to take each of these expressions and multiply them by this time dependent function e to the I omega t, then what would the resulting functions look like over time? Well, because the idea is, as time passes, you can think of whatever's multiplying this. The absolute value of it would be, think of it as like the amplitude of a wave. And if there's some complex exponential multiplying this, like e to the I theta for some theta, that plays a role of a phase shift. So, okay, so if I take these two and multiply by e to the I omega t, the amplitude is given by these expressions, the absolute value of these expressions here. And because they don't depend on time, then we have what's called a standing spherical wave. On the other hand, if I were to take these two and multiply by e to the I omega t, then I'll give an example. So e to the I omega t, take the first one, hn1. So that is approximately, so I'll have minus I, x in denominator, and then what I'll have here is e to the I, then I'll have x minus n I 2 minus, plus omega t. Okay. So what happens is this omega t causes a translation. So what's happening is this wave that we see here is now propagating because of this plus omega t term in the imaginary part of the exponent. It's the same effect as you see here, e to the I x plus omega t. Right? A function of this, how does this behave as time advances? This function describes a wave that is propagating to the left because we have x plus omega t. If you were to look at the real imaginary part separately, that's what you would see. So it's because of this plus or minus omega t going into the argument that makes it a traveling wave. Whereas we don't have any such effect, this kind of translation when we multiply these by e to the I omega t. That's why they're called standing wave. Guess if I were to be formal about this. Standing waves, not so interesting. Spherical waves, traveling waves, interesting. Actually, I think I might. Okay. Like I was looking some things up about standing versus traveling waves, while preparing this. And oh, that should be a 2 right here. Whoops, that's what I get for copy and pasting carelessly. All right. Okay. Because if you were to plot these, okay, if I multiply by e to omega t and plot, then really what you'd be plotting is either the real part or the imaginary part as a function of x, and then seeing how it behaves over time. So you'd be updating your plot over time, but what you're viewing at each fixed time is a function of x. And if you did that with these multiplied by e to the omega t, you wouldn't actually see the waves change, but these you would, because of this shifting that's taking place. So it's really a plot that shows this standing versus traveling. Now, orthogonality. The Bessel function, regular Bessel functions, capital J, they have this orthogonality property that was previously established. That if you evaluate the Bessel functions of order nu, at these arguments that involve the zeros of this same Bessel function, then if you use different scalings corresponding to different roots of this Bessel function, then resulting functions are orthogonal. So this inner product will turn out to be 0. Where the p equals q, then this is the expression that you get. So we can use this orthogonality relation for regular Bessel functions to get a orthogonality relation for spherical Bessel functions, just by the definition of spherical Bessel functions. We can substitute that in, and this is what we get. So it's very similar in appearance, where it uses the zeros of little jn, but there's one significant difference here we're pointing out. Here we have its factor of r squared in the integral, whereas with regular Bessel functions, we had rho to the first power. Now rho is the change in variable factor for changing from Cartesian to polar coordinates. R squared is the radial part of the change of Jacobian change to spherical coordinates, which makes sense because we're dealing with spherical Bessel functions. And because we have r squared here, we end up with an a cubed here as opposed to an a squared in the case of regular Bessel functions. So I'm going to show an example where Spherical Bessel functions come into play, solving a PDE. And this is a time-independent Schrodinger equation, phrased as an eigenvalue problem. So the solution of the Schrodinger equation is this wave function psi. So it describes a particle of mass m in a sphere of radius a. The quantity capital E here, that is an eigenvalue because we have operator applied to psi is equal to a scalar times psi. So capital E is an eigenvalue of this operator, so this scale Laplacian. And the way you interpret it is possible value of a particle's energy model here. We have these boundary conditions that it must. So we're working on the sphere of radius A. So wave function has to be 0 on the boundary of the sphere, and it cannot be singular. So inside the sphere, it must be well defined or finite. Now, if we try to solve this PDE using separation of variables, I won't go into the details here. I've done that with a previous PDE, the Helmholtz equation. So you get an ODE for the radial part as a function of R. And this equation we've seen before is the same radial equation that we got before, where the solution is spherical Bessel functions. Oh wait. Okay, I apologize. It's not an ODE that we've seen using separation of variables, but what we do get is the ODE that's satisfied by the spherical Bessel functions of argument KR. Now this is similar to what happened with regular Bessel functions, where with other PDEs, you form separation of variables, and you have ODE depending on the radial variable. And the solution in that case is a regular Bessel function evaluated at k times r. K squared is the eigenvalue. And you, what that's equal to is if you take all of these constants and move them over to the other side. That's your eigenvalue k squared. K squared was found previously to be the eigenvalue associated with the Bessel equation. Now, the solution has to be a scalar multiple of this spherical Bessel function, where the scaling constant k has to be equal to this, because of the boundary conditions. If I set r equal to a, then that a is going to cancel with this a, and what you're left with is a 0 of a spherical Bessel function, so that the whole thing will be 0. And that means this boundary condition is satisfied. Now suppose we want to find the minimum energy possible. Because we can solve this across for all different values of L, and the solutions would be spherical Bessel functions of a first kind of all orders. So what would be the smallest value of E that we can find? It turns out to be the smallest positive 0 of J0 of x. Now, J0 of x, that was previously established to be sine of x over x. But the smallest positive 0 of that is pi. Now, k is supposed to be equal to a 0 of your Bessel function divided by a. In that case, that 0 is pi. So k squared is equal to pi squared over a squared. But k squared is also supposed to be equal to this from the original eigenvalue problem. So if we set these two equal to each other and solve for capital E, the energy level, the energy value, then this is what we get. So this is the smallest possible energy that you can have that satisfies the boundary conditions. Questions about what happened here? Now, I mentioned one orthogonality relation for the spherical Bessel functions, but here's another of a different sort. Because the previous orthogonality relation had spherical Bessel functions of the same order, though with different scalings of the argument. Here we have spherical Bessel functions of different orders with the same scaling of the argument. In this case, no scaling at all. So if we integrate from minus infinity to infinity, that scalar product, instead of from 0 to a, we have this orthogonality relation. But we don't have a counterpart like this orthogonality of regular Bessel functions of different orders. Now, this ODE right here, oh, that should be a Z, not R, is almost a Bessel equation, but it has a slight change. The Bessel equation has a plus here and a minus here. But if we change these signs, what we get is the modified Bessel equation. Now, the regular Bessel equation has the solutions of the Bessel functions of the first and second kind. Similarly, the solutions of the modified Bessel equation are the modified Bessel functions of the first and second kind, and they're denoted by I and K, as opposed to J and Y from the regular Bessel equation. So for certain situations from using separation of variables of PDE, where in the separation of variables, you're equating certain expressions to a constant, called a separation constant. And in most cases, the separation constant is negative. But there are cases where it's not, due to a different sign, and that's where the modified Bessel equation comes about. So from this equation, that comes about from a separation of variables process, where we change signs, we get the modified spherical Bessel functions. The little I and little k defined in terms of half integer orders of big I and big K. But notice the scaling factor is different here. We still have x in the denominator, but here we have 2 over pi instead of pi over 2. That's a little strange. These modified spherical Bessel functions satisfy these recurrence relations, which come from similar recurrence relations for regular modified, that sounds like an oxymoron, but Bessel functions, and I refer to capital I and capital K. It occurs to me when I was preparing these notes that I want to cover everything that was in the section on spherical Bessel functions. There's a separate section in chapter 14 on these modified Bessel functions, and I realized, wait a minute, I didn't cover that section. Oops. So I brought in only enough of it to introduce this. don't worry, there's no homework on this section. But put in the schedule, so we're gonna cover. At least no one's making me, but still. Now this is with the regular spherical Bessel functions. You can work out relatively simple formulas for at least the first few. And that's what we have here. But notice that whereas the spherical Bessel functions involve sine and cosine, the modified spherical Bessel functions involve a hyperbolic sine and cosine. Essentially what you end up with is kind of like the spherical Bessel functions with a complex or imaginary argument. That's how we get these. On here, the first few modified spherical Bessel functions of the second kind. And if you were to let x be small or large, this is how these kind of functions behave. Using a similar approach to how these were obtained for the regular spherical Bessel functions. And notice that whereas the little j n and little y n, we had e to the ix or e to the minus ix, but here it's because e to the x or e to the minus x. So we have exponential growth and decay. Hey, Jenna, where'd he go?
I'm here on a different device.
Oh, okay. Sorry, that'd be we just felt like that, so I just found it funny. But I mean, I see you happening all the time of students leaving and coming right back. So. So he was taking around even though he was reaching into the nose. So it might not have been a bad time to leave. Okay. All right. Okay. I was speaking about previously in these notes when I was discussing standing waves versus traveling waves. It's possible that I said something that mathematically was incorrect in my attempt to convey what I saw in various graphs of these kind of waves. And I feel like if I try to fix stuff, I'll just make it worse. But maybe something like
correct you.
What?
We can't correct you.
Something I benefit from considerably in teaching at USM. Well, okay. On very rare occasions, I can be, but unlike, for instance, if I'm teaching at Stanford, where that's a problem. I have to be a lot more on my toes there.
So you're welcome.
Yes. Oh, yes. I'm definitely grateful. Yeah. I probably shouldn't even said anything. But it is going to bug me. So, and I will feel the need to address it later, even though there's no homework in that section. But, What?
For yourself.
Yes, definitely. Yeah, because this is a section that last time I taught this class 9 years ago, I didn't come to this section. I asked Dr. Zhu to do it. And then did not find homework on it. So go ahead, you guys. Okay. What about homework questions? Yes.
14.1.8.
14.1.8. Okay. Recently looked at those, but see how it goes. I was scrolling too far and I went down to like chapter 22. Oh, that's how I went to the 2-page view. It's like, I never want that. Won't take the hint. Okay. Unshare and reshare. Okay.
Okay, so like for the recurrence relations, do we just do direct substitution with b minus 1 and b plus 1 into the like summation formula of the Bessel equation?
Okay. So okay. Let's do this. All right, for this one right here, they mentioned like show by direct differentiation, but you wouldn't need that for um, this one. Yeah, so when you substitute nu minus 1 in here, okay. I'm making a mistake of trying to do this problem in my head. It's been a while since I've actually looked at it. Okay. So what do you want to do? For example, when you substitute nu minus 1 for nu in here, but what you want on the right side involving this is x over 2 to the nu plus 2s, but when you from here you're going to get nu minus 1 plus 2s. So what you want to do in that case is do some factoring. And you might find it, I can say one definitely needs this, but don't rule out the possibility of needs to do an index shift of some kind. Probably more likely for this other one, probably a derivative.
Yeah. So when we substitute nu minus 1, do you have to do anything with the gamma function in the summation, or do you just leave it as a
Okay.
like it would be s plus b and then like plus 1 and then like minus 1?
Okay. Yes. So yeah, if you can have nu of s plus b in one case, and then s plus b plus 2 in the other case. One thing to check out here is gamma function properties. case any of those might be helpful. Considering how it relates to factorial and such. Okay, hold on. Oh, okay. Because one thing to keep on is he's wondering how this factor of nu gets introduced. So a probability gamma function which generalizes its relation to factorial. And I wonder if I can edit this. I don't want to do that. Not gonna let me do that. Okay. No, but in general, gamma of z plus 1 equals z times gamma of z. So what happens is when you work out these, you're gonna have gamma functions evaluated at different arguments. But here you have a single argument, and that's how I can relate it to. Any questions about this one or another one?
You say it properly.
Okay. Gamma of z plus 1 is equal to z times gamma of z. Yeah. So that's a generalization of the fact that for integer n, someone needs to mute themselves. Victor, you're making noise.
Yes.
Oh, your question. Okay.
Yes. Homework question 7.6.14.
Okay. So this case, fine to make noise. All right. Okay.
All right. So I'm finding it difficult to apply the Leibniz formula in finding the derivatives.
Okay. If anything, this full Leibniz formula is overkill. Because one thing, you're not going to need this term in this problem. Really, it's just going to boil down to this, and that. So, for instance, when you take the derivative of this whole thing with respect to x, okay, so you're going to use product rule, but when you get to the point where you're going to take a derivative of this entire integral, because it has x as the upper limit, what that means is the derivative of this integral is going to be this integrand where x is substituted for s throughout. So that's really the only way in which Leibniz formula comes into play in this problem.
Okay.
Well, okay. Similarly, okay, so let's suppose we're taking the first derivative of y2, alright, so then this will come about like I just said. At some point, when you take the second derivative of y2, this that you obtained from the first derivative where x is substituted for s, you'd be taking the derivative of this. So at some point you'd be taking a derivative of this integral, and there again you're going to have so p of x will eventually result after many layers of differentiation, which makes sense because you want a p of x to appear.
Okay.
Okay, any further homework questions?
So for the gamma like thing that you said earlier, what if it's like s plus r plus 1? Would it just be s plus r on the outside then?
Okay, I just go to the page where I'm getting all this.
Yeah, because I think I know what you're talking about.
Okay.
I just wondered.
Yeah, there is a generalization of a property of escape. I guess you use an inductive argument to extend it or apply that property repeatedly. Okay, let's see. Where do I have that? Okay. Okay. Yeah, so here's the property. Oh, dang it. Here's the property I was telling you about. And now the generalization of it, and that's what leads to this factorial relationship. The generalization of that is further down. Where'd it go? I know I saw it here. Dang it. Where did it go? Oh, okay, I didn't scroll through far enough. Okay. This right here is how you extend it if you add something more onto the argument in this one. Okay. Anything further? Oh, I'll have this up. Okay, here we have the schedule. Now, of course, when I made this schedule, I, like all my colleagues, were not aware of the impending football-related cancellation. We were all blindsided by that one. Okay, so I will not be covering this. Oh, well, I know this doesn't mean anything, but I shouldn't have it there either. I'm not sure what I'm gonna do schedule-wise. Because something's gonna have to fall off the edge. Or it's possible that these topics I've split over 2 days might not really take that long. Okay, I'm gonna go with that. That might mean having to delete a homework problem, but I don't think anybody would find that either.
Work what you feel is best.
Okay.
With our interests, for us, your end part.
Yeah.
That's for us.
Yeah.
Last grading.
He's on top of us.
Yeah, oh yeah. It helps everybody. Well, my real dilemma is that from when I taught this 9 years ago, I do not have a full set of notes. Like the stuff I just did on Spherical Bessel, I had to write that new. I have some notes for some of these other things, but they're not really as complete as what you've seen before. So
You have homework assigned with them?
I do, yeah. But what happened 9 years ago was that the semester drew to a close. I got is that a dog barking? Okay. Everybody. Oh no, they're all still here. That's weird if they're not. Okay.
They're both muted. The dog happened.
Okay. I know Taylor's the dog. So. I don't know. Okay. It's a mystery. At some point I got tired of writing full-blown notes, so then so laziness stage one was I would just write a document that only had the math in it, like the equations that I knew I needed to cover, and I would just say something in between again. And then I got lazy level 2 was I would just photocopy the pages from a textbook and just hold that while I wrote on the board. So.
You know, we should do that with our homework. We should go through the same with.
So my plan is to this time around to write proper notes. We'll see how that goes, and if I guess in interest of fairness, if I end up somehow delivering less, then I have to let you do the same. So, what that means, I'm not sure yet. As a reminder, I think I had said, I think the undergraduate dropped 2 homework assignments, and graduate students 1. Okay, so there's some leeway there, but yeah, I don't remember. I forget exactly where my notes were now. Like I think I don't have anything at all for chapter 18, so good time ahead. Okay. Oh, let's go to chat. Oh, okay. Got an apology from Chandler. No apology needed. I thought that was entertaining. Yeah. All right. So I guess I'll see you in a week.
No, I'll
So we would have this pattern.
see you tomorrow.
Yeah, see you tomorrow. So that's that. This thing having pattern like also.
Yeah. Can I meet with you Friday?
Oh, yeah.
I'll see what.
Okay. Oh,
Hey, Doctor.
yes, Chandler?
Oh yeah, I was just pretty much gonna say the same thing Dale did, but a little different. But yeah.
Oh, but what exactly? I'm confused.
About classes being canceled on Thursday. Is that like all classes?
Yeah, okay, so what happened was, there was an email sent some time ago that, we were holding a nationally televised football game here on Thursday, and they decided, to just close the rest of campus operations down. So all classes at both campuses, in person or online, are canceled. And they did not tell us this until the semester was already underway and all of us had already planned to teach on that day. So, whoops.
That's very southern of them.
Yeah, it's very USME.
Because.
So there you go.
The 15th. So.
I'll probably be doing something else. Instead of joining the game, but. Alright, so,
Okay.
go ahead.
Yeah.